So I'm Dr. Donna Arnold, and I teach both chemistry and forensic sciences at the University of Kent, and I interact with all year groups, and I teach a variety of things, really. So today we're going to look at some of the chemistry. I'll hand you over to Stefania, and she can introduce herself.
Hi everyone, my name is Stefania, and for this year I'm SPS Student Ambassador and SPM BAME Ambassador. I'm here if you'd like to ask any questions, if you want to know what uni's like or anything about that. I'm here for support, anything you need.
Thank you. Excellent. So I will attempt to share my screen, what I hope will be a taster on a chemistry lecture that normally goes out to first years. So if you bear with me a moment, I've probably got far too much open as usual. So like I said, this is a lecture on states of matter. It normally goes out about normally next term, beginning of next term to first years. So normally when I give a lecture, I didn't want to deviate too much. I wanted to give you a bit of a real feeling of what lectures with me might be like, or lectures with any academic might be like, but I didn't want to bore you with some of the details that maybe are less important here. So normally my first few slides, I give some information that enables students to put the current lecture in context. So I'll link it to the pages in the textbook, the chapter references, so that you can go and look some things up yourself if that's what you want to do. I'll talk about the details of any material to be covered over the course of the lectures. So this was one of 6 lectures that I gave in a succession, and I'll normally give any details of an assessment. So I normally start talking about the assessment long before it's due, so you guys have a chance to think about it and ask lots of questions of me. It's really important that you guys ask questions. This is what we want. So as this is a taster lecture, I've taken out some of the bits and pieces that we'll look at. Like I say, it's first year, so we're going to look at states of matter, phase diagrams, ideal gas laws, and then we're going to move into non-ideal gas laws. As this was the first lecture, I don't tend to give any recaps because it's the first part of the material. So we normally jump straight in. So that's what we'll do today. So first of all, we have to think, what are the, let me, I have a laser pointer now. So what are the states of matter? Well, there are 3 states of matter that we're going to be really interested in over the course of this lecture series. And these are solid, liquid, and gas. So let's think about these in a little more detail. So we have our solid. This is a diagrammatic representation of our solid. Our atoms are all packed in quite tightly, so we know that it has a fixed shape and a fixed volume. So if I freeze an ice cube, it will have the shape of the ice cube holder, so it will be a cube. And this is at a certain temperature and pressure. So we know that we can control what state of matter we're going to get by temperature. For example, if I fill up an ice cube tray and I put it in the fridge, it's going to stay as liquid water. If I put that same ice cube in freezer, I'm going to get ice cubes. It's going to freeze. If we think now about a liquid, we know that it has a fixed volume. So like I said, with the solid, it has a fixed shape. So if I put that ice cube in my drink, it's going to stay square until, if it was at a constant temperature, it would stay square. If I took a bottle of Diet Coke and I tipped that into a glass, my liquid would now take up the shape of the glass. So it has a fixed volume. It's still going to have the same amount, but it's going to take the shape of the container that I put it in. It's quite fluid. It can move around, hence I can tip it from one container to another. And again, this is at a certain temperature and a certain pressure. If we now think about gas, well, we know that it's also fluid. It moves around. We can't see it as much, but we can move it around. And it spreads out to fill whatever space it's in. So it no longer has this fixed volume, and it no longer has this fixed shape. So it will spread out to fill the container. So if I put it in a stoppered conical flask like I have here, it will have this volume, but if I take off the stopper, it's going to fill to expand the room, and it will have the volume of the room. So let's just quickly look at some characteristics of some liquids and gases and solids. So we said that it has a definite shape. For a solid, it can resist this deformation. Liquids have no definite shape, so they assume the shape of the container. And then gases fill the container completely. We can't really squidge a solid, so we can't compress it. It has no compressibility, or it's nearly incompressible. If we have a liquid, we can slightly compress it, but gas, we can squidge it to fit into a smaller container. There's some densities here, so usually higher density than liquids. Liquids have high density and gases are low density. Solids are not fluid, they don't move around very much. Liquids are fluid, gases are also fluid. Solids can have an ordered arrangement of molecules. They're packed quite close together, so they tend to order in a nice fashion. Liquids tend to be disordered and have clusters of particles, and gases consist of extremely disordered particles, and there's much empty space in there. If we think about how much things can move, we can have particles can have vibrational motion only, so they just can move a little bit within space, they can't move lots of way. Liquids, they can move in 3 dimensions, but they might collide with each other. There's still a chance of meeting another molecule. And if we think about gas, they can have rapid, random motion in 3 directions. So how can we think about this in terms of something a bit more exciting? So let's think about a concert. Right? So this is an outdoor festival. It happens to be download. And we can see the same states of matter at a concert. So if we look at the very front of a concert, people are densely packed. There's not much dancing room. You can maybe bounce up and down and jiggle, but you're only going to vibrate with those around you. You're quite densely packed. So this is like our solid, right? If we think about the middle of our festival, and there's a little bit of more room, we can dance around a little bit, but there's still quite a high chance that I'm going to bump into somebody as I jump around and I dance. So this is more like the liquid. Very back of the festival, there's a lot more space, we can jump around a lot, there's plenty of room to move, and there's not much chance that I'm going to collide with somebody else. So this is more like the gas phase. So you can see, we can see how we can think about the crowd being densely packed near the front, less densely packed, but still quite a lot of people in the middle, and fewer people and less densely packed in the back. So now that we can think about that, we have that in our head, we can start to think about these things in different ways. So first up, let's think about a solid. So if I have all of these atoms, they're all quite close together. And if I have something like sodium chloride, so this is sodium chloride, the gold colored atoms are sodium and the green colored atoms are chlorine. So just nice table salts. If I look at that, we know that that's a solid. If I look at that if I could get close enough so I could see what exactly the atoms were doing, I would see that they line up together in an ordered array. So every time I look at a chlorine, it's surrounded by sodiums. And if I look at a sodium, it's surrounded by chlorine. And if we boiled that down to the smallest repeat unit, so if we looked at the whole big pattern and we can boil that down to the smallest repeat unit, we call that a unit cell, and that's what's shown here. So you can see, in order for me to be able to keep repeating this, I have to start at one chlorine and another chlorine, and then from chlorine to chlorine and chlorine to chlorine. And if I stacked all of those up on top of each other in 3 dimensions, I would end up with this ordered solid. And we call this long range order. Solids don't have to be crystalline. Most solids are or have long range order. What we can also have is situations where we don't have long range order. So if I looked in this little region here, I can see that my silicon, in this case in the gold, and my reds are my oxygen. You can see actually there's quite an ordered array here. But if I look wider out, you can see that that order dissipates. And we call these things like amorphous solids. So what this means is they lack long range order. So they have pockets of short range order, but they don't have the long range order. And this is something like glass. Glass has no crystalline structure. And crystalline structure will become important as we go through the rest of the year and through into next year, indeed. So we need to think about how we now move between these three states of matter. So we've got our solids, liquid, and gases, and we refer to these as phases. So if we want to have a phase change or a phase transition, this is essentially the change between one state of matter to another state of matter. And in order to do that, we have to overcome the attractive forces that are holding it together. So we need to either put energy in or take energy out so that we can make those attractive forces or break those attractive forces. So if we look at something like our solid, which we have here, we know that if we heat a solid, it turns into a liquid. And we know if we heat it some more, it turns into a gas. And that if we go back the other way, we can take our gas to our liquid, to our solid again. And of course, a good example of this that everybody knows is water. So H2O. If we take our ice at 0 degrees C, we melt to form water, and at 100 degrees C, we boil to form water vapor. And what we need to remember is that this occurs at atmospheric pressure. This is 1 atmosphere. So here's a question. So do you think that all water molecules enter this vapor phase simultaneously? So if I hit 100 degrees, does my whole liquid just dissipate straight away and become a liquid, become a gas, sorry? And normally this would lead to some class discussion, perhaps some putting up hands to see who can answer that, perhaps some suggestion, but we can go to the answer here as I can't see the Q&A quite so easy when I'm in the share screen mode. So the answer is no, because some of the molecules at the surface, they have enough energy to escape the surface before we get to the boiling temperature. So they're able to overcome and escape into the vapor phase. And this is our interface between the air outside and our liquids. So they start to escape. And just like that, when we go the other way, some materials condense before we get to our boiling point. So we need to think about, we said a key thing there. We talked about pressure, and we said that that was under atmospheric pressure. So we need to think about what happens when we start to have pressure in the system. So if we heat a liquid and we heat it, it becomes a gas. So, okay, what happens if we take a gas at constant temperature and we compress it? So again, this would be a point where we would take some answers from the class and see what they would be able to say. And of course, the answer is, as we compress it, we go to liquid. And this is how we get to things like liquid helium, which we then use in MRIs or other medical devices. We take helium gas and we compress it to make a liquid. So that means that now we have two axes that we can start to consider. And what we can start to think about now is what we call a phase diagram. And a phase diagram tells us the temperatures and the pressures that each of those phases adopt over which range. So we can start to understand for a chemical component whether we would expect it to be solid, liquid, gas under particular conditions. And this is really important if we're going to use this industrially. If perhaps we want to use a liquid to dissolve something in, it's very important that we know what temperatures its liquid is at. Or if perhaps we need a gas to power a gas turbine or something, we need to know these things. And what we end up with is pressure, which you'll sometimes typically see in atmospheres, but also in pascals. It's more also common, depending on when the phase diagram was published. And we have it against temperature, which typically is in Kelvin, but again, you may see it in degrees C. And what we end up with is a region of the phase diagram, which is our solid, a region of our phase diagram, which is a liquid, and the region of our phase diagram, which is a gas. And so I can say at this temperature and this pressure, I would expect my material to be solid. So let's look at a phase diagram. Here's the phase diagram for water. We can see that we have pressure along here, we have atmospheres, and then we have our temperature along here, which we have degrees C. And we can see that at melting temperature, we're on this line here, which is our equilibrium between ice and water. And we can see here, if we draw another tie line, these are called tie lines, at 1 atmosphere and 100 degrees C, we're on this line here, the boiling point of water. So the eagle-eyed among you will see, if I just flick back, this diagram has this solid liquid line going this way. However, however, the water one has it going this way. So why is that? Water's very unusual, and this is very unusual. Most materials have positive slopes, but water actually has a negative slope. So if you put into your ice cube tray your water again, and you also put another liquid in a different ice cube tray, when you put those in, the one with water will expand. So it has a larger volume when it takes the ice than it did as a liquid. Whereas most liquids have a smaller volume, they contract as they freeze. And the reason for this is hydrogen bonding. So water makes a nice network of hydrogen bonds. It actually means that ice has a bigger volume than the liquid, the water. So there are two other really important points on this phase diagram that we need to talk about a little bit more. So we can see here, this is called the triple point. And at the triple point, we have solid, liquid, and gas all in equilibrium together. The other important point is this point up here. So this is above a temperature and a pressure, we get to the critical point. And above this, we have what's known as the critical region. And we'll come on to that in a couple of slides time, and we'll talk about the critical region a little bit more. But these are important things you need to remember. So let's look at another phase diagram. Actually, phase diagrams can be a lot more complicated than just solid, liquid, and gas. So if we look here, we have what is the phase diagram of sulfur. And you can see that we actually have two different solid points. So both this area here is solid and this area here is solid. And the difference between these two solid areas is the crystal structure. So those arrangements of atoms that we were talking about are slightly different. So that long range stacking order is different between the two. And you can actually see this visually if you look at sulfur. When it crystallizes, it's very pretty. If we look at the orthorhombic form, it has these cube type crystals that grow. If you look at the monoclinic form, they grow as needles. So we can actually see the difference between those. These are known as allotropes. So many things have allotropes, such as allotropes of carbon, where we know that carbon can adopt lots of different structures as well. We have liquid, and then we have our gas here. So the big question is, where is the triple point? I can see lots of places where I have multiple phases in equilibrium. Well, the answer to this question is that the triple point is still the point where we have solid, liquid, and gas in equilibrium with each other. So here we have solid, solid, liquid. Here we have solid, solid, gas. So the triple point is still where we have solid, liquid, gas in equilibrium. The three different phases, we can have multiple points where we have multiple equilibriums, but there is only one triple point. We can also go back and look at our phase diagram of water. And what we can actually see is we looked at this bit down here, which was nice and easy. We just had ice, liquid, and gas. But actually, if we look quite a lot different, we see that at high pressures, we have lots of different forms of ice. So water can form lots of allotropes as well. And there's a lot of work being done to study these materials because it gives us understanding of how space evolves and things like that. We can actually access some of these at high temperature and high pressure. And people dream up really exciting experiments to try and find out the different structures of these materials. I promised you that we would come back to the critical point. And if you look here, I said the critical point was above that point, we end up in the critical region, so above a given gas and pressure. And what we end up with is if we end up with a state which has the properties of both a gas and a liquid. So we end up with one indistinguishable phase. As we move along that solid liquid gas line of the phase diagram, if we were to look below the critical point, we would see two distinct phases in equilibrium. So we would have the liquid and we would have the gas. As we increase both the temperature and the pressure, this distinction becomes more and more blurred, as you can see here, and we end up with what we call a supercritical fluid. So it's one indistinguishable phase. And supercritical fluids are really exciting because we can actually get properties of both gas and liquid, like I said. But that is really interesting. So this is some work I did a very, very long time ago now. But we took a membrane, which you can see here, which has lots of holes in it, and we wanted to grow materials in them to make new electronics devices or new exciting ways of doing things. We were looking to make some wires, and we were looking to make them so that they had a core and a shell. And using supercritical fluids, we can dissolve the precursors that we wanted to use in the supercritical fluid as if it was a liquid, so we can dissolve, make a solution. As we pass it through our porous material, our material with lots of holes in it, it behaves more like a gas. So the gas flows through the holes much easier, and we're able to grow these very pretty nanowires. So just some key points with just some key points on phase diagrams before we move on. So we know that boiling point increases with increasing pressure. So these are some important things we need to remember. We know that melting points usually increase with increasing pressure, but there are some examples that don't do that, some exceptions, for example, water. And we know that many systems exhibit polymorphism and show allotropes, such as our sulfur, and we were talking about carbon. So now we need to start thinking about things a little more. So we're now going to expand these ideas into looking at how things behave when we're looking at closed systems and volumes and things. So we're going to start to consider that. So we're going to consider the relationship of volume with temperature and pressure. So we said before that we had our liquid, and when we heat it, so if we have a piston in here, as we heat it, the piston will move up and our gas will adopt the whole volume. If we plot this as a graph, so we're just going to plot volume against temperature, we have this straight line. And what we can say is that volume is equal to a constant times the temperature. So we can give this a constant. If we have our gas and we have our piston and we now apply pressure and we're going to compress this, you can see we compress it. And if you remember, we said that it eventually goes to liquid, but we can make the volume smaller. We can plot volume against pressure, and we end up with this kind of exponential decay. And we can write this mathematically, and we can say that our volume equals a constant times 1 over the pressure. Okay, so this starts to lead us into trying to understand how gases behave. And the behavior of gases is reasonably well understood. And there's a long history of lots of different scientists investigating it. And then back in 1662, I mean, hard to conceive that this work was being done that long ago, Robert Boyle did some work on gases, which basically led to what we now know as Boyle's law. And what he said was at constant temperature, the pressure times the volume is equal to a constant. And what this is a macroscopic law. So we've made no assumptions about the microscopic system, so what the system is, and we've not considered the concept of atoms or molecules at all. Okay, we're just literally taking an arbitrary gas and we're saying that the pressure times the volume is equal to a constant. In a bit later on, the volume of gases was studied by Gay-Lussac, and he led to Given-Charles law, which is the scientist that inspired his work was Charles. And what he said was that constant pressure, the volume is equal to this V0 term, which is effectively the volume at 0 degrees C, times 1 plus alpha T, where T is the temperature and alpha is the coefficient of expansion. And alpha is typically found to be about 1 over 270. And the modern value is 1 over 273.15. And for the eagle-eyed amongst you will know that that's the conversion rate to convert degree C into Kelvin, so the absolute temperature scale. So we can see here, we've already stated that a volume of gas, if we have constant pressure, it will increase linearly. We showed that. So we know that volume is directly proportional to temperature. And if we plot volume against temperature, you can see we can extrapolate the straight line. And what we will get to is minus 273.15, which is absolute zero or 0 Kelvin. So if we think about these a little bit more, so we know Boyle's law describes the behavior at constant temperature, and we have P times the pressure times volume is equal to a constant. We know that Charles' law is at constant pressure, so this gives us volume over temperature is equal to a constant. And if we combine these two equations, we get PV over T is equal to a constant. And this is an equation of states, and you will have met the concept of equation of states earlier in the lecture block when we talked about thermodynamics. And this leads us to the ideal gas law. And what we know is that the ideal gas law is given as PV equals nRT. And this is a very important law, and it's really important that you guys remember this. What we end up with is our P is our pressure, V is volume, the N is the number of moles, R is the gas constant, so this is our constant, which has a value of 8.314 joules per mole per Kelvin, and our T is our temperature. And this means that we can start to work out the differences in temperature, pressure, and volume between two gases. So we can actually write like this. So P1, V1 over T1 is equal to P2, V2 over T2, where the 2 tells us that's gas number 2, and the 1 tells us that's gas number 1. However, so this is great. We have a way to calculate things. This is really, really good news. Unfortunately, real gases do not follow the ideal gas law, particularly at high pressure. Some obey it better than others, but unfortunately, it turns out that it's not a good law. But it is, however, a good approximation. So it tells us information. It's nice and easy to use. So now we need to think about, well, what's the problem? Okay, so why do real gases not behave? So we have, for 1 mole of ideal gas, so all I've done here is rearrange the equation we had on the previous slide. We know that PV over RT equals 1. And if we plot PV over RT versus our pressure, we've got lots of different gases here. We know that an ideal gas would give a straight line because that's the ideal behavior. If you look, helium is not so bad, that does give us a straight line. But if you look at something like CH4, so methane, you can see that there is a really large deviation. You can see that we have quite good linear behavior at high pressures. But at low pressures, but the deviation, this effectively works out as low pressures, and at high temperatures, the deviation is much smaller. So what's wrong with the ideal gas law? Why doesn't this work? So from Charles's law, we know that the assumption is that at 0 K, the volume of a gas is 0. Okay, so at absolute 0, a gas has no volume. But we know this cannot physically be true. If I have a series of marbles and I compress them, I can only compress them so far. I'm never going to be able to compress those marbles to have no volume at all. The same is true for the gas. There are molecules in the gas. They're never going to have 0 volume. So this simply just cannot be true. There's always some volume there. And this means the law works at low pressures when the molecules are far apart. but at higher pressures, when we push the molecules close together, they start to interact with each other. And then this means that this law fails. So what we're saying is that the ideal gas law neglects intermolecular forces. And we're going to talk about intermolecular forces in the next lecture. So can we improve the ideal gas law? Well, of course we can. So you can see here, this is the pressure that's observed, and this is the ideal gas law. So we can see that typically the ideal gas law overestimates the real pressure, which is a good thing, because if I'm building a system that needs to withstand a certain pressure and I calculate it with the ideal gas law, I've got a buffer area. So this is why we still use the ideal gas equation. If it underestimated it, I could be in trouble because things might go bang. So what we need to do is we need to improve it by adjusting the pressure to account for intermolecular forces. And we also need to adjust the volume to account for the volume of a molecule. So we have some different versions here. There's the van der Waals equation, which is quite commonly used. And then there's Berthelot's law equation, which is also used. And you can see here, these are more complex. Berthelot's law takes into account temperature. We have minus NB term, which is the effective free space that a molecule can move in. And we also have this NB term, which is effectively the molecular volume. We also have this now, this AN squared over V squared. And this is a effective reduction in pressure due to the intermolecular forces. And this is because as we get stuff closer together, the attractive forces are going to pull the molecules back into the container. And this reduces the pressure. So we have these two equations. If we now go back to our list here, we can see that this is our observed pressure. This is, again, is the pressure calculated with our ideal gas law. And what you can see here is that the van der Waals equation gives a better assumption, but actually it slightly underestimates. So it's still not a perfect match to this. And this is why we prefer to use the ideal gas law sometimes, because it gives us that little bit of buffer space. So next lecture, what we're going to start to look at is how we can use those, how we can start to make calculations with these, and how in the real world do we use these to get information. And we're also going to move on to starting to look at intermolecular forces, and that will start to lead us into looking at liquids in a bit more detail. It's always a good idea to just give a quick summary. So today's lecture, we will have looked at states of matter, and we've looked at phase diagrams. So it's really important you start to understand the important points on a phase diagram. And we've started to talk about ideal gas laws and non-ideal gas laws. We'll start to look at some actual mathematical examples and calculations of how we'll use them. And that's the end of today's lecture. Get back my Zoom window. And then hopefully I can see the chat and see if there's any questions. I can't see any at the moment. So perhaps I can, no, just everyone confirming they could see. So perhaps I could ask Stefania some questions. Perhaps she would like to join the webinar. And perhaps she can tell you a little bit of what it's like to be, you know, what year she's studying in and what it's like to be a student at university, and give us some insight into how she finds lecturers. And I've stood at the front of a room teaching.
Yeah, that's no problem. I'm in third year now. I actually started on our foundation year. 1 second, I think the music is too loud upstairs. Let me just, yeah, so I started in foundation year. I'm currently in third year. They always say that the jump between second year to third year is the greatest. However, you guys are not there yet. So for first year, from sixth form, because I actually did the foundation year, the jump between foundation year and first year was quite big for me, just because I felt like in foundation year they basically spoon feed you the information rather than go and look for it for yourself. So that's the one thing I would say. You're definitely going to have to be more independent with everything you do in uni. However, the lectures are there to help you. They're actually amazing. All you have to do is ask for help. They will go through great length just to give you what you need. And I really mean it. I know you might be shy to ask for help at first, everyone is, but I promise you, as soon as you make that connection with the teacher, from there on, you can just keep on asking questions. You will not feel awkward. They treat you like human beings. They don't see you like students. It's just nice. I can definitely say that. Yeah.
We want you to do well.
Thank you. Yeah, Ken was definitely not my first choice. And at first I was a bit disappointed, but I'm actually very happy I came here. I don't think I could have had another support like this anywhere else. Honestly, yeah. 10 out of 10.
Thank you. Yeah, so all of the lecturers are always happy to answer questions. We do answer through email or one-to-one. Obviously this year has been a little bit different with how we tackle these things. Technology is sometimes our friend, and as you can see, we also have struggles with technology sometimes. So we also do run, so this year we've been running a chemistry drop-in session, and students email questions in advance, so that it's actually me who runs it with a postgraduate, so that we have time to put proper examples together rather than trying to answer a question on a fly and dream up something on the top of my head. So we're able to put presentations together, we're able to put these online, we're able to find extra material. We have a Moodle.
Was it you, Dr. Arnold, that started the forum on Moodle?
Yes.
Yeah.
Yeah. So there's forums where you can ask questions anonymously, so that, you know, that takes that little bit perhaps of interpretation out of it, of thinking I should know that. There is no such thing as a stupid question. If you don't know the answer, I maybe didn't explain it well enough. And sometimes all it takes is for me to think in a different way, or to explain it in a different way, or to point you to a different book. We also have what we call Moodle, which is where we put all of our notes for you so that you can go on and access them and stuff. And we have one that is dedicated to just putting up extra material that we find. So it could be videos, it could be quizzes, it could be extra lecture notes or pages that somebody else has put on the internet. So to try and give you a wide range of resources that you can access to do that. Typically lectures, they expand on each other. So like I said, this lecture would have normally gone out to first years in week 13, which for us is the first week back in January. And some of the stuff like equation of states, so some of those words maybe didn't mean anything to you guys, but they will have been explained beforehand. And it's perfectly acceptable to ask more questions and say, actually, you know what, I'm still not quite sure where that comes from. It's the only way to learn. Does anybody have any questions? Is there anything you wanna ask about studying or about approaching? Both Stefania and I are happy to answer whatever we can answer for you. The last one is that our Zoom wasn't working particularly well. I hope you enjoyed hearing about solid states of matter and starting to think about gas laws and starting to think about how these do. Like I said, normally as we move through, we start to, this was very much the introduction lecture, and then the next lecture that follows this, we start to look at the equations a bit more and start to sort of say, well, okay, if I know this, what do I calculate? And why would that be important? Why on earth would I want to know what these things are? I try to give you some idea that, you know, these are important. It's important we know what state something's in if you're going to use it. But we start to look a bit more at why do we need to know this? How does this actually relate to the real world that we live in? And what is that important? And that's some of the joys of chemistry, right? You get to You know, we sometimes forget we teach all these laws that were uncovered in 1664 and think, why do I need to know that now? But it's still so important for how our industry works, or how we use materials, how things in hospitals work, or, you know, so there's this underlying knowledge base, but then there's just this exciting use of what these things are used for, or even, you know, what the next generation, what you guys will come and learn chemistry, and then what you guys will take on and take technology forward. And, you know, some of this stuff is incredibly important for green chemistry and environmental chemistry, and how we move to sustainable technologies and sustainable living. You know, as moving forward, you know, these laws were all used to build the basis of how we make our fuels now, but we're going to have to rethink how we make our fuels, so, or how we do manufacturing, or how we do this. And these laws will be important again as we start to think about, well, if I switch that for that, it will use less energy and put out less carbon. But then I still need to know, will I blow up my pressure vessel if I, explosions are not fun for pressure vessels. So any questions at all?
Can I just ask something, Donna? Because I know that, you know, lots of students do come in to us when they email in. And one of the things I always ask them about, which is quite a worry, is things like assessment patterns and things like that. You know, they're, especially in the first years, they're very concerned that they're just going to get like a whole, you know, they've come out of school and they're just going to get a whole heap of assessments. So you know, could you explain that to us, please?
Yeah, certainly.
Thank
so
you.
We try very hard to make sure that you're not hit with heaps of assessments. Unfortunately, assessment is part of the game. Some of that is, we can't help you if you don't ask us questions as well, right? But we can monitor assessments and see perhaps where a student is struggling. They're not just there to make life difficult for you, they're meant to make life helpful for you. And it also helps you think, where am I struggling? The assessment patterns are all laid out before the start of term, so you know exactly when your assessments will be. And we have set number of assessments per what we call a module. So a group of lectures is called a module, and you'll have 8 different modules that will cover different things. For chemistry, it's maybe organic chemistry, inorganic chemistry, physical chemistry. We have labs, of course. Chemistry is a lab-based subject, and you have to learn to write those up. But assessments typically build on each other. So lab reports, we build to the point that the big one that you need to be able to do. Mark assessments and things are all on Moodle. Everybody is absolutely approachable for questions beforehand. So, you know, make sure that you know, don't leave your assessments till the last minute. It's really tempting, but if you've got questions, much better to go get them out of the way first off. Many lecturers, myself included, I will start to explain. So this is lecture 1. This is a 6-lecture block. The assessment was due at the end of the 6 lectures. So I was already starting to explain in lecture 1 what the assessment will be, when it will be due. You guys should be familiar with your timetables too, and your assessment patterns are part of your timetable. But most lecturers already starting to say, this is what you can expect your assessment to be. But we work very hard to make sure that they don't cross over, and each module will have a set number of assessments, and then of course the exam at the end. Some modules don't have an exam. They will be 100% coursework, which means the assessments through the year, they're all worth a little bit and they all add up. I mean, Stefania might be able to comment a bit more from the other side of what it's like to have to do assessments.
So I remember when I first started uni, I was very scared that we're going to be a lot of work to do. It's actually not like that at all. Well, no, let me not say that. There is a lot of work to do, but if you do sort out your timetables, organize yourself, the workload is not actually that much. I feel like A level was much harder. Uni, the work, because you're only doing chemistry, everything is connected together. If you are able to put all the lectures together, being on top of your work, you will not fall behind. You will find everything so easy as one lecture just connects with the other. Same thing with labs. Yeah, just start early, never leave it last minute, because what happens usually, all the deadlines are together, and then you're just left with tons and tons of work to do. I've done that many times and I've learned my lesson. So you have to just literally just start the work as soon as it gets to you. And anytime you need help, just ask for questions. Just ask. As everyone will just get back to you straight away with all the help they can give you.
We also have a very good academic advisor system, which is you're assigned effectively an academic mentor at the beginning, and you can talk to this person. They're not there, they can't help you with everything. Unfortunately, when you get to university, teachers tend to be a bit more specific. So there's no point asking me organic chemistry questions because I don't know either. But what they're there to do is point you in the right direction. But they can also, like for my academic advisees, they come see me, they have their meetings with me, and they'll say, my time management skills are not very good. How can you help me with that? And I give them advice on perhaps how they can manage their time better, or how to approach tackling something that is stressing them out. And we try and talk our way to make sure that it's less stressful to tackle some of these things. I mean, you have to remember, right? You've got to do them, but I got to mark them. So, you know, and there's a lot more of you than there are one assessment for you, and that's 100 assessments for me. But, you know, they're there. We all want you to do well, and we all want to support you in the transition from A-level to your school to university. And then we want you to go out and do well. The assessments are not there to trip you over or to make you do badly or to make you feel bad. They're there because we need to make sure that the knowledge is getting through and that the understanding is getting through. And we need to make sure that we can then help you when you come with questions. Because it's not really good to come to me and say, I don't understand any of it. Because firstly, my experience is that that's never true. There's always, you always understand way more than you think you do. And secondly, that second bit is, if you come to me and said, I've tried this, I don't get that, I can work out what it is that you don't get, and I can help you to understand that. And ultimately, what I want for you guys is to have that aha moment where chemistry clicks and you think, actually, you know what, this is cool. This is fun. I do want to do this for the rest of my career. I want to be a chemist. It is fun. There's so much different bits to it and so many different facets that you can go and enjoy. It's certainly fun. So it's getting over this fear that we're just mean people who are there to set you assessments. That's not the case at all. Some of my colleagues have queues out their doors, and you know, that's not at the moment. Obviously, nobody can queue anywhere, but except outside the supermarket, I guess. But you know, we're there to help, and you know, we certainly always make time for students. And it's no bother. If you speak to some of our students, they spend a lot of time having a chat. We're people too, you know, we're approachable people too. And there's a great supports team behind the scenes as well, who are there to help you with more different things, maybe pastoral, or, you know, where to find this information. There is an incredible, great team at the library who are there to help you learn how to use the library properly and how to find books. And of course, a lot of stuff has moved e-books more, but you know, we still have that big building in the middle of campus full of books and full of resources. We must remember that, you know, books are not the only resource anymore. That's the olden days when it was books. Now there's the internet. There's so many places we can go for resources, and your academic advisor can help you with some of that and help you start to do that. We have a lot of things in place to try and help you. You know, you have to take some responsibility for the learning process. You have to learn, but we're there to try and guide you and help you and push you in the right direction.
Thank you, Donna. And the other question we get asked a lot that seems to come in on emails is, if I do chemistry, where does this lead me to? You know, an employability, you know, can I just be a chemist, or is there a whole world of things where I can go and I can take my chemistry degree?
There is a whole world out there of chemistry, and every facet of life has chemistry in it. You know, there is no place that chemistry, obviously the big chemistry thing this last 7 months or 10 months has been a vaccine. So there's obviously all the pharmaceutical side, that's all chemistry. I'm an inorganic chemist, so there's a lot of companies that specialize or making materials. So obviously, you know, the flip side of trying to make things less carbon polluting, more greener, We have to think on our feet. We need new materials to be able to do this. We need lithium. There's all, you know, chemistry is everywhere. When I first graduated from my degree, I did chemistry. Initially, I was thinking of going into medicine. So there's roots into, you know, chemical medicine, biochemistry, those kind of things. I ended up working in a pharmaceutical company making anti-cancer agents, which turned out not to be what I needed to be doing, but that's a different story. But then actually when I applied, I found that I applied to a dairy because they needed chemists to check the integrity of the milk. I applied to a whiskey distillery. My dad is still very disappointed with that job.
I'm with your dad.
Yep. But there's whiskey people there. If you look around, I wish I'd been a bit smarter and asked these questions myself. There are chemists in Formula One that get to go around the world with the teams because they need to check the integrity of those parts, and that's chemical engineering. So, you know, it may sound like a different topic, chemical engineering or biochemistry or medicinal chemistry or materials chemistry. They're not, they are chemistry. They are using the same equipment that we use. I actually do some work now. I'm actually given another webinar later in the week on heritage science. So actually we're using chemistry and the techniques that we look at our chemical materials with to preserve the Mary Rose, which is Henry VIII's warship. So, you know, chemistry is really wide. There are chemistry for everything. It's additives, it's in food chemistry. It really is something for everybody. We just have to learn the basics so that we can do all of those exciting applications. I can sit here and I could keep throwing out different examples in aeronautics, in space, in, you know, my colleague at work, she's interested in micrometeorites. She's a physicist, but the stuff that we were talking about together is just chemistry and the chemistry of life. They're interested in amino acids and things and how life started in space, but effectively that's just chemistry underneath there. Chemistry underpins, I'll probably get in trouble for saying this, underpins the other sciences. It's got its foot in everything.
I'm waiting for the everlasting chocolate bar. The chemist that makes the everlasting chocolate bar's got my vote.
But it's all in, you know, in chemistry of taste, the chemistry of smell, perfumes are all just chemistry.
Yeah.
It's everywhere.
There is a perfume, isn't there, that's out there, isn't it? It's just a number. And apparently when you put it on, it's because everybody's chemical makeup is different. It smells different on absolutely everybody, but you can't smell it yourself. And I think I'll have to look it up. Yeah, it's amazing. It's something like, I don't know, say H20 or, I mean, it isn't that, but it's something like that. But fundamentally, it works solely on your own skin.
Yeah. And that's
very interesting.
Yeah, and that's all just the chemistry of interactions again.
Yeah.
So, you know, these chemistry is just everywhere. And we also teach forensic science, and chemistry is a huge component of forensic science and forensic analysis. Really, the world is your oyster. You know, you find the bit of chemistry that you like, and then a few years from now, I'm not going to tell you how many years from now, but a few years from now, you could be sat in this chair, swinging it, because that's what's good. And you know, telling people the chemistry really is exciting. It may seem hard sometimes, but what you can do with it is so much fun. I wouldn't do anything else in the world.
I want to say, once you really understand the chemistry behind stuff, it gets very exciting. Yeah, once you finally see how the molecules can just come and build up something like, I don't know, like a phone, like with nanoparticles or stuff like that. It's really very interesting. It really opens your eyes.
Yeah, effectively chemistry of materials is why we have mobile phones instead of great big things on the wall, you know, that we're not still dialing each other from the living room or the kitchen. They used to be in the kitchen.
With those massive, great big curly lead that used to get longer and longer because you used to just uncurl it as you used to drag it. See, you're too young, all you people that are listening at the moment, but Donna and I remember those days. The curly lead day.
Yep. So, you know, and that's just materials. That's effectively what my research is. I'm interested in materials for the next generation. How do I make things faster, smaller, less power hungry, so that you don't have to charge your phone every day? Because that would save the battery, and that's greener.
That would be lovely.
Yeah, brilliant. Are there any questions as we're moving? It's now 8 o'clock. I hope everybody's enjoying. I mean, I just think it's phenomenal. Thank you, Donna. It was so interesting, and Stephania. So are there any questions by our attendees at all before we let you go home? Any questions? I know everybody gets ever so kind of nervous and they think, oh, I don't know. But if you hope we've covered your questions so that, you know, that you don't feel that you know you've come away with a question in your head. We haven't, but you can always email us in as well. Okay, don't be afraid to email us. Okay, any final last questions there? No? Okay, well, on that note, if it's okay with Stephania and Dr. Donna Arnold, then I think we'll leave this meeting.
Yeah, thank you for coming. I hope you enjoyed that.
Thank you. Thank you, everybody.